All right, we begin vectors. As we just said, a vector is a way of showing or working with both magnitude and direction. And eventually what we want to think about is this idea that if I've got, for example, an airplane traveling like that, and I've got a wind traveling like that, what's the impact? Like, how do we know what's going to really happen if we've got an airplane traveling like this and the wind like this? And it turns out that vectors do a beautiful job of analyzing this. If in fact we put one of them on the origin in standard position, and then we put the other one tail the tip, this resultant vector turns out to be where the plane would actually go. In other words, this is the direction he's heading, and the magnitude is described by the length of him. This is what the wind is doing, and the magnitude is described by the length of that. When you add these vectors, you can just see tail the tip what the true destination of the airplane would be. And we'll be able to calculate this angle and thus find the direction of travel. And we can calculate the length of this, and that'll be the magnitude of the resulting speed of the airplane. So that's where we're going with this. But in order to get there, we got to get through some stuff first. Let's define and talk about what vectors are. So the first thing is a vector is described with an arrow, where P in this case would be the initial point, and Q is the end or terminal point. Vectors are typically denoted using the arrow symbol, and I like to put the little half barb on it, although you're okay using the double barb. Like, to me, that looks like a vector really cleanly, as opposed to a ray, which would be the double barb. And again, there are alternative ways of doing this. You could also just do a single from the initial point with a vector note on top. And this says a boldface lowercase letter. I'm not sure I've ever seen that, but we're going to use that for this worksheet set anyway. So what do we want to know about these vectors? Well, the first thing is its magnitude. In other words, how long it is. If that tells me the speed of the aircraft or the number of newtons of force we're experiencing, we need to be able to calculate it. And because it has this opportunity to be broken down or decomposed, as we'll learn about later, I can actually treat it like a distance. Does this look like a distance we've done before? How would I find the distance from here to there? The distance formula. So this magnitude formula is exactly derived from the distance formula. If we've got a vector with an initial point of x1, y1, and a terminal point of x2, y2, then we can find the magnitude of v, also known as v with a double absolute values on it, by taking the square root of the sum of two quantities, each squared. This one is x2 minus x1. This one is y2 minus y1. Does that remind you of the distance formula? Pretty similar, right? So for example, if I want to find the magnitude of this, I'd say the magnitude is equal to the square root of two quantities squared added together. Which values go here in the first spot? The x value. So the first one, -7 minus 8, and -2 minus -4. Whenever solving, we do the inside of the parentheses first. So -7 minus 8 is -15. -2 minus a -4 is the same as adding 4. So that's a +2 squared. So that's going to give me 225 plus 4, square root of 229. And let's give ourselves a decimal approximation for that. because we want to be able to compare this reasonably with other things. We'll just round to the nearest hundredth. So I get 15.13. And of course, the units are going to be determined by the context. Right? Is this miles per hour? Is this Newton's force? Okay, how's that feel? Any questions on that? 5, feels very doable. 3, a little challenging, but we'll do some practice. 1, I don't get that. Okay, good. It's going to ramp up from here, so hopefully that part's easy. Second thing we want to do before we actually talk about working with multiple vectors is understand what the relationships are between various types of vectors. We can have two vectors that are parallel, that are equivalent, or that are opposite. Parallel vectors mean that they are going in same or opposite directions, but don't necessarily have the same magnitude. But their slopes are related. In other words, these two have the same slope. Does that one have the same slope? It does, doesn't it? If I go from the tail, or the initial point, to the terminal point, I'd go down and left, which would be a negative number for the y and a negative number for the x. But as a fraction, that's going to cancel out versus going positive right and positive up. So these actually will experience the same slope. And so we can know that the slope is the primary indicator to tell us whether multiple vectors are parallel. Then we've got this idea of equivalent vectors. And that's kind of like congruent, meaning it's got to have all components the same. It is both the same magnitude and the same direction. So that's going to be both finding that their magnitudes are equal and that their slopes are the same. And then we've got this idea of opposite vectors, which is where they're the same magnitude, but going in exactly opposite directions. And interestingly, are these going to look like equivalent vectors? If we just compare slope and magnitude, it would, wouldn't it? So we have to be careful about these two as a distinction. Because even though they share the same slope, they're not going in the same direction. So let's take a look at A and E here. Here's A, and here's E. If I were to calculate their magnitude, I would go delta x of 2, delta y of 1. So it'd be 2 squared is 4, 1 squared is 1, 4 plus 1 is 5. The magnitude is the root 5. Is this the same magnitude? Yep, still 2 and 1. And if I did the slope, it'd be a rise of 1, run of 2. So this slope would be up 1, left 2, positive 1 over negative 2. This slope would be down 1, right 2. Both those slopes come out the same. But we can see that the arrow here is going this way, and the arrow here is going this way. So what do we call the pair of A and E? Parallel, equivalent, or opposite?
Opposite.
Good, opposite. So you'll have an opportunity to practice visually with that, and then you'll have an opportunity to do the same thing, but now quantifying. So you'll find the slope formula. Do you remember the slope formula? y2 minus y1 over x2 minus x1. You'll use the slope and the magnitude formula we just did up here with these values to determine whether these two vectors are equivalent. Any questions? So now we know kind of what it is. How do we use them? Well, floating out in space, vectors can't really interact very well together. So it's super helpful if we anchor them in a standard position before we do our calculations. And standard position means the initial point is on the origin. So you can see here we've got an initial point that's anchored on the origin, and the arrow then sends off a direction for us. And this kind of reminds you of the unit circle, right? When we did the unit circle, we discovered that by having a unit length of 1 here and a theta as an angle, this coordinate at its tip became really important. What was the x value of a coordinate in the unit circle? Cosine theta. And the y value was sine theta. Okay. And those became critical for us, and they still will now. When we want to talk about the component form of this, in other words, show this vector with its important features, what we'll do is use the vector is equal to these brackets that are like arrow pointed, and we'll list the x and the y of the terminal point. Why is this so important? Well, for the same reason that we've had such importance with the cosine and the sine, is that the magnitude can be found from these. How would I find the magnitude of this particular vector given A, B as its terminal point? What would the magnitude of V be? You guys are quiet today. It's a right triangle, isn't it? Yeah, go ahead. Square rooted, right? Square root of A squared plus B squared. It's the Pythagorean theorem. It's the distance formula. It's all those things. So that would find us the magnitude if we're given in this component form. How would we find the direction, what the theta is off that polar axis or the x-axis? What's the relationship between this angle and the opposite side and the adjacent side? Thank you. The tangent of theta is going to equal the opposite, b over a. So if I want to find the magnitude and direction of this, I'm going to find the magnitude first, and I'm going to use this formula. Square root of 7 squared plus 24 squared, square root of 49 plus 576. 576. So this is the square root of 625. 25. So the magnitude is 25. Oh, yeah. Another Pythagorean triple, 7, 24, 25. And the direction, I'd say that the tangent of theta is equal to b over a. So theta is equal to the inverse tan, 24 over 7. Should I do degrees or radians, you think? Probably degrees, because if it's radians, it's going to have like pi wrapped up in it that I can't really see. So I'm going to choose degrees. And then I'll go second tangent of 24 divided by 7. And I get 73.74. Now, remember when we talked about the restrictions on domain and range associated with inverse trig functions? This was going to give us a certain value. Is that value where we want it to be? If I'm looking at 7 on the x and 24 on the y, I expect to be up here in this quadrant. And so, yeah, 73 degrees, 25 distance, that sounds reasonable to me. This is what I'm looking at. Something kind of like that. Make sense? Questions? Okay, so you'll have 3 opportunities to practice that skill. Now, with the same concept here, as we said, anchoring this thing in standard form is really helpful. When we can put it into standard position and have it in component form, we get a lot of opportunity to interact with these things. But it might be given to us at some other points, like x1, y1 as the initial point to x2, y2 as the terminal point. How can we translate it to get it into standard position? Well, what we know is that any vector can be written if it starts at x1, y1 and finishes at x2, y2. Any guesses? It's going to have to be written with those pointy brackets, but the x value and the y value are going to come about as a result of x2 minus x1 for the x value and y2 minus y1 for the y value. But in the grand scheme of things, the function is, or the coordinate is going to have those and a comma. So let's try number 7. Let's find the component form for this vector. So we'd say CD is equal to 6 minus 3, comma, 3 minus 5, which is equal to 3, comma, negative 2. And now that we've got it in component form, could we find the magnitude and could we find the direction? Okay. You guys with me? 5, I feel the path we're going along. 3, I'm losing sight. 1, are we going somewhere? Okay. So once again, we talked about what a vector is. Its magnitude and direction. It's expressed by this arrow. We can find the magnitude by simply taking whatever the x displacement is, squaring it, adding the y displacement squared, and taking the square roots, the distance formula. And then we talked about naming it by the terminal point's coordinates when it's in standard position. And now we talked about moving it into standard position if it is initially not there. So we'll play a little bit here with equivalent vectors. In other words, I'm going to have you create a vector AB in component form, right? Which means you're moving it over to the component form, which is in standard position. Do the same with this one, then calculate the magnitude and direction and see if they're equivalent vectors. And you might not even need to do equivalent vectors. I mean, magnitude and direction. Let's see, what would AB be? What would AB be? What would its size be? I mean, not our size, its component form. -7 minus -3, comma, -2 minus 6. So -7 minus -3 is plus, so -4, -8. What is this? What does this coordinate here represent? Take a moment, talk to your neighbor, see what you can come up with. What does this represent? Go. Okay, what is it? -4, 8 is what? -8. Caleb?
Wait, it would be if you.
Beautiful. If you move that vector to the origin, standard position, this is its terminal point. So what would we expect CD's point here is going to be if they're equivalent vectors? Yeah, -4, -8 should be the same. Right? We wouldn't need to do magnitude and direction because it'll show us with these two values exactly the same thing for it to be equivalent. It could be parallel and go in a different direction. But let's see, if we do -1 minus 3, comma, -1 minus, -9 minus -1, this is -4, this is -8. What do you know? So yes, equivalent. What if I had a third one like xy and it was 4, comma 8? Be an opposite vector, wouldn't it? Because if I did the magnitude of this and the magnitude of this, they come out the same values once squared. But this one is going -4, -8, going down in the left direction. This one's going +4, +8, up in the opposite direction. Okay. So what can we do with vectors? Well, it turns out we can do a lot of the things we normally do. We can multiply vectors, but you can't multiply vectors together per se. But if you've got a vector that is going in this direction, you can multiply it by what's called a scalar, which is a numerical value, a number value. So you could double it, you could cut it in half. You could multiply it by a -1, which is kind of cool. That makes it go opposite, makes it an opposite vector. You can also add vectors, as I was describing. If you lay the first one in standard position, and then you make the second one go from that tip as though that's its new standard position, your result is the sum of these vectors. And what's fascinating, and we'll get to this in a second, is that the A value of V, or the X value, plus that same X value of W will combine to be the X value of the new point. It makes it really easy to add two components that go in different directions. And you can subtract it, basically the same as adding a negative value. So in the event that we have a scalar multiplication, in other words, some integer or value, doesn't have to be an integer, it can be a fraction or positive or negative, times the vector, it will give us the coordinates distributing through effectively. K times A1, comma, K times B1. And if we do addition of vectors, because one vector is written like this with its x value, and the other vector is written like this with its x value, the sum of them, any guesses? What would the x value be? A1 plus A2. And the y value would be B1 plus B2. And the same concept works out for the subtraction. A1 minus A2, comma, B1 minus B2. So let's take a look at number 2 here. It asks us to add vectors A and B. So when I add, I'm simply going to add the x's, the A values. So -6 plus 1, and I'm going to add the y's. 2 plus 7. -5, comma 9. This is my resultant vector, as they call it. Does it almost seem too easy? Waiting for the other shoe to drop. One more little piece. In the event that we can do a scalar multiplier of a vector, there's value in our understanding the vector, like the unit circle, in a form, a similar form, the right direction, but a magnitude that's only one. Like the unit circle was so valuable for us. We're going to look for something called a unit vector. And if you think about it, let's say that I had a vector that was up here at the point 4, 3. What's the magnitude of this vector? Five. Thank you. 3, 4, 5 is a Pythagorean triple, so you should remember this is 5. If this is 5 units long, and I've got the coordinate ending here, the terminal point, how could I find a spot here where this length is 1? Divide it by 5. It's exactly right. We would take, if this is vector W, for example, I would take vector W and multiply it by 1/5. In other words, we'd get 4/5, 3/5, and it would proportionally stay the same direction, but it would change the magnitude to be a single unit value. So a unit vector is a vector with a magnitude of 1, and given any non-zero vector, a unit vector u in the same direction can be written as 1 over the magnitude of v, just like you did. You found that the magnitude was 5, and then distributing it across the components of the vector. The magnitude of v, 1 over that, times v. Let's take a look at number 7. If we want to find the unit vector, we know it's 1 over the magnitude of v times v. So what do we need to find first? Magnitude of v, which is square root of -5 squared plus 12 squared. Anyone know this one offhand?
13.
13, good. 5, 12, 13 is another one of our Pythagorean triples. So that means that the unit vector will be 1 over 13 times -5, -12, positive 12, sorry. And so it will just be -5/13, 12/13. That's with me? That's where we're stopping today. We'll continue on Thursday with the rest of it. That's an introduction to vectors.